represent motion with dots and vectors. That's what I want to do. So in order to represent dots, what I have to do here is that I have to introduce the variables of motion here. So we need to introduce the variables of motion. And we'll do this in step, but essentially I have to get to displacement, velocity, acceleration, and time. Those are the 4 parameters that we got to talk about here. So you're going to see that I'm going to spend most of my time on displacement and velocity and time, and then acceleration is really at the end of the chapter, but then we really get deep into it in the following chapter. So let's go look at this thing here. So here we go. So the first thing I need to talk about then is I need to talk about position / displacement. Now, I know that you know all these parameters in some shape or form. My job is to make sure that we put it into the language of physics. Okay, so here we go. Position is a scalar quantity. And when I say the word scalar, what I really mean here, it's just the number. Right? Like 1 or 3.6, it's just a number. It doesn't give you anything else here. So position is a scalar quantity and is the physical location of an object. And what I mean by that, let's set up a coordinate system. So if I set up a coordinate system like this, and one of the things that you could say here is that let's say that I define the origin. Well, position in this case, I could put an object here and let's count squares. So if I count squares, this guy, assuming that this is the plus direction and this is the negative direction, the position of this object from here to here is what? That could be 2 squares. Do I write +2? No. Because as soon as I write a plus or a minus sign, that's not just a number. By the way, could I have put this guy right here? Yeah. Why? That's 2 squares from here. So when I'm thinking about position, I literally mean its location with no information other than that. All I know is that at each of these points, it's 2 squares from the origin. So that would be a good example of what position is. But what we're interested in is displacement. Displacement is a vector quantity. So a vector quantity, I should say here, is not only a number, it's a number and a direction. So what you're going to see here is it has, so I'll define these here in a moment. It has what we call magnitude and direction. And what I mean by that, it has two characteristics. A scalar has one characteristic, it's just a number. A vector quantity has two characteristics. It has magnitude and direction, which I have not defined yet. But that represents the change in position. So displacement is about the change in position. So let's look at that. So what you're going to find here, so if I start to kind of put the language in, what do I mean by this? When I write the word displacement, I always mean two things. The first thing is, how far did you go? And when I write, how far did you go? What this really means that this is what they call the magnitude. And sometimes the magnitude is also called the length. And the other piece of displacement is which way did the position change? And when you look at which way the position changed, what this is really telling me is it's telling me the direction. So when I say the word displacement, that's what I mean by that right there. And you're all experts at displacement. I'm not telling you anything that you don't know. I may be saying it in different words, but here's what it means here. So let's set up a change in position. So you could imagine that I have a number line. And let's say here that this is a location of where we're going to define our origin. So up here, we started at some point 1. And since we're talking about a one-dimensional thing, I'm going to call that the x-axis. And in this case, I'm going to say that that means the positive direction. And in this direction, that's going to be the negative direction. Do I have to choose it that way? Textbooks tell you that you should choose it that way, but that doesn't mean that it's right. You are the ones that are in control of your coordinate systems. Don't let textbooks tell you which coordinate system to use. And I'll explain that here in a minute here. But check this out. Let's say that this is our initial position, x1. And now this object changes position. Let's say that you move your car from 2 squares all the way to, let's say, 7 squares. So this is 3, 4, 5, 6, 7. You get to right here, and then I'm going to call this 2 here. So if I look at the position of this object, we agree that the position of this object from here to here is 2 squares. And if I count all the way to here, this is 7 squares. So what you're finding here is that the displacement must be the change in position. Okay? So when I look at the displacement, we saw when we say the word how far, this is the same as the change in position. And in this case, we say that the difference between this guy is going to be what? It's going to be 7 minus 2, because that's how many squares I moved, right? So when I look at this, that means that this is the distance that I moved. And we could clearly see that the change in position in this case is 5 squares. Now note, that does not tell me whether I change 5 squares to the right or to the left. I need an additional piece of information to tell me which way. So if I look at which way, this tells me the direction. And the direction, what we said here is we said in the right direction. And if we're going to the right, we typically give that with a plus sign. So what you're seeing here is that my displacement really looks like this here. So I have something called the displacement, and there's two characteristics to it. One, it has this thing called 5, right? So if I start at x1 and I change 5 squares, how did I change 5 squares? Did I go to the left or did I go to the right? We went to the right, so now we put the plus sign here. So in other words, this tells us about the direction, and this tells us about the magnitude. But this is a pain in the ass to write sometimes. So how do we draw this as a picture? The way we draw this as a picture is we draw an arrow. So the arrow starts at x equal to 1, and then it moves to the right. How many squares? It moves 5 squares. And so this arrow, which is 5 squares, you could see that the length of this guy, which is also called the magnitude, is 5 squares. And since this is, there's only 2 directions that you can go, you could see here that because this is the tip here, it points to the right, therefore we give it the plus sign. That's what we mean by this guy right here, right? That's what we mean by that. Any questions so far? Okay, so then let me show you about some of the notation that I wanna use here. And what I wanna use for my notation here is that it goes like this here. Instead of symbolically, sort of like always focusing on numbers and stuff like this, what I'm going to do here is that I'm going to do the following thing here. I'm going to come in, and if I have a short vector versus a long vector, to conceptually try to get the idea across, look what I'm going to do. I'm going to draw a little x. And then if I have a long one, I'm going to exaggerate so my displacement is bigger. So that's how I'll do that to communicate that piece of information. Okay, let's go to the next piece. So now that I got displacement, I want to then go in and focus on the next piece, which is we want to talk about speed/velocity. Again, you know everything about speed and velocity. I don't have to tell you this. My job is to do what? Get it into the concepts of physics, right? That's my job. I want to get it into the concepts of physics. So here I go. So the first thing that I want to do here is that it turns out that speed is a scalar. And remember, scalar means what? It's just a number. It's just one number, just like position. But velocity is a vector. So what I mean by vector here, it has to have magnitude and direction. So here we go. So a very simple definition of speed here is that speed is what? It's the measure of how fast something is moving, right? Like I had to tell you this. Of course you already knew that. Right? So what we want to do here is that we want to really focus on looking at the physics of this thing. So now, here's what you find. So, but speed mathematically looks something like this here. But if I look at speed, what you're going to find here is that speed is encased in velocity. So what you're going to find here is that the symbol for speed is v. And remember what I said, it's embedded in velocity, just like position is embedded in displacement. And what you're going to find here is that this is really distance divided by time. And the way we write this is we write the distance, remember, is the displacement. I have a change in distance, and I have some time interval. So when we write speed, we write it this way. And this makes sense here. As an example here, you could drive a car 50 miles per hour. But what does 50 miles an hour means? It means that you drove 50 miles in 1 hour. So you could see that clearly that's displacement. And then this is your time interval, just as you would expect it here. But it turns out that the worst possible units for doing science is the miles per hour units as far as speed is concerned. So what we do here is that we use the metric system, which is defined as the MKS system. Of units. And then the MK system, what you find here is that this tells me is that the M stands for meters. So that's our distant unit. The K stands for kilogram. That's our mass unit. And the S stands for second. And those are the only 3 units. Actually, that's not correct. There's a 4th unit. So when we start talking about sound, there's an intensity unit. That's not here, but it's actually, you can write this in terms of the MKS system. So every quantity that we're going to deal with this semester, its base is in meter, kilogram, and second. So what's the unit for velocity here? So then the units of velocity, and the way I describe a unit is that a unit of velocity, we put brackets around that quantity that we want to do. So what's the unit for velocity or speed? Well, it has to have a unit of displacement. It has to have a unit of time. But we know that a unit of distance is a meter and a unit of time is a second. And so therefore, our velocity or speed has units of meters per second. Okay? So now, What do I mean by this here? You're going to see that how I write speed is about, the way I like to symbolize it is using the same type of notation that we did in the previous chapter or the previous section here. So as an example of how I want to look at this thing here, let's think about two different speeds. We want to compare two speeds. Well, if I write 5 meters per second, let's say that I take, let's say that 1 square, so the distance of 1 square equals 5 meters. Okay? So what this means here, that if I look at the length, so that means if I have an object that starts here and moves all the way to this point, then that means if this is 0 seconds and this is 1 second, then this means here that I've now traveled, right? That means that my delta x over delta t tells me that I traveled 5 meters in 1 second, or 5 meters per second. So when I look at my dots here. I started my time in here and I ended it here. So then this length right here represents 5 meters per second. But what if I have an object that's traveling 20 meters per second? If it's traveling 20 meters per second, if 1 square is 5 meters, then that means that this guy has to have traveled what? 4 squares. But if you look at 4 squares, that means the distance that it traveled in from 0 seconds to 1 second has to be that long. So what you're seeing here is that this v is a little tiny v because it only traveled 1 square. But this guy did what? A much higher speed. So when I draw it small, this means that this was a slower speed. When I draw it big, this is a faster speed. So it's nice to symbolize it because then without too much detail, we could just say, yeah, we know that's going faster because the v is bigger. The length of that arrow is bigger. So now, the last thing that I want to do here is that there are 2 categories of speed and velocity. There's the first one here is average speed, and the second is instantaneous. So what do I mean by average speed? Well, when we say average, we really means that you're averaging over a combination of slower and faster speeds, right? That's what you mean by that. So like, I live in Watsonville. When I used to drive to Cabrillo and Aptos to teach, even though the speed limit is 65, during rush hour, there's no way in hell you're going to be driving 55 miles an hour, 65 miles an hour. Sometimes I'm driving 30, 40, sometimes I'm driving 65 miles an hour. But the way we count the average velocity or speed is that we talk about the total distance divided by the total time that it takes you to get there. But the instantaneous speed, this guy tells us that this is the speed at 1 instant of time. So if you're driving down the highway and at 1 instant of time, you're going 80 miles an hour on Highway 1, what are you going to tell the officer? But wait a minute, my average speed is less than, 80 miles an hour. You should only give me a traffic ticket for my average speed, right? Yeah, good luck to you. It turns out that in physics, we typically don't care about the average speed. We care about the instantaneous speed. That gives us information at one particular time. So when we talk about instantaneous, this is what we're most interested in physics. So when I talk about speed or velocity, I always talk about instantaneous velocity. So let's write down velocity now. So my definition of velocity, because it's a vector, what we say here is it tells us about how fast something is moving, and then we got to talk about which way. Right? So we got to talk about two things. And what you're going to find here is that the how fast tells us about what? The magnitude. And which way tells us about the direction. So here we go. When we write velocity, we take our velocity variable and then we put an arrow on top of it. Some people put full arrows. I happen to draw a half an arrow. And so what you're going to find here is it tells us two things. There's plus or minus. What does the plus or minus tells us? It tells us about direction. Am I going to the left or am I going to the right? And what you're going to see here is that because we're interested in the instantaneous velocity, it's typically the derivative of the displacement vector. And this guy here tells us about the instantaneous speed. So how fast is really about speed at that split second. And which way is the plus or minus that tells us it goes to the right. And what you're going to find here, that this quantity here really tells us about, so if I look at this thing, the magnitude in this situation, which is how fast, is really the slope of the x versus t graph. And that's how we really get the velocity at that point. It's the tangent to the position versus time curve. And then the direction, what it does here is it tells us about the sign of the slope, if I could say that, right? Because the slope has a magnitude, and then it tells you whether it's plus or minus. And the sign tells us, of course, whether you're going to the right or to the left. So that's what we mean by velocity right there. So when I box this up, this is our definition of velocity.